Who's doing the PLS tutorial? Some. Okay. I'm just going to do it. Um, okay. So who knows partial least square or have heard of it before? By name. Sometimes. Okay. So just heads up, this will be a stats class. So be ready for that. But I'll try to make it as friendly as possible. Okay. So multivariate data. Anyone knows about multivariate analyses data? You've heard of it before? So what is your understanding of multivariate data? Guess.
We're
Okay.
looking at multiple variables predicting other multiple variables and their relationship.
Yeah, that's pretty accurate. So usually in our data, we have, for example, if you have questionnaires, you have images, or even brain data, you work with multiple variables, right, instead of one. And traditionally, we do like, oh, a correlation between X and Y, but now when you have multiple of them, you have more things to consider, right? The main thing that we have when analyzing it with like correlation or other univariate analysis is you need to correct for multiple comparisons. Remember this from your stats 101? And that brings like every effects away. So multivariate analysis takes care of that because it analyzes all the data together. And so you takes into account the underlying correlation between them. So it's also something that you use every day. So if you've been on Google, you've been on Spotify, YouTube, that's how they extract like the most important, the recommended list for you based on your history. So they're trying to extract the most relevant information for you. So what is it like to work with multivariate data? Some common characteristic with about multivariate data is that usually there are many more variables than observations, and this could cause some issues when running univariate analysis. For example, regressions, where when you're trying to predict something and you have more variables than your people, then you tend to overfit your data. And also, traditionally, the statistical analysis that you learned from Stats 101 cannot handle this type of issues. The other issue is that when you work with multivariate data, you have a lot of variables that usually don't meet the assumptions of traditional statistics. So for example, I don't know if you remember the hypotheses, no, like not hypothesis, but yeah, the assumptions for your traditional t-test and ANOVAs. Like you assumed your variables are homogeneous, which means their variance are the same. Their errors are normally distributed, or when you compute a t-test, it follows a t-distribution, right? So those are the assumptions that you usually have. But nowadays, with rich data set, especially multivariate data sets, sometimes those are not met, right? The criteria are not met, which means if you run the univariate analysis, there will be an issue. So I'm also going to talk about inferential tests that's non-parametric, which means it doesn't assume the distributions of your data. So you don't need to meet those criteria. You don't need to assume that, oh, it's going to be distributed like a t-distribution, and you could just base on your own data to decide whether it's significant or not. So that's another thing we're going to cover today. And so the goal of multivariate analyses and also for PLS today is we're extracting the most important information. So I have thousands, tens of thousands of data, but I cannot like look at them one at a time, right? I cannot just go through brain voxels and check each of them one at a time. So what multivariate comes into play is trying to extract the most important information from like this mountains of things. So partial least square methods. Partial least squares methods are the multivariate methods that we use to look at correlation between two sets of things. So it comes in two format. One is the regression. So if you want to predict, for example, I want to predict my behavior with my brain, then you will use partial least square regression. If you're looking at correlation, if you want to look at commonalities in the behavior, you would do PLS correlation instead. So these are methods that have been widely used in not just brain imaging, but also econometrics, chemometrics, psychometrics, ecology a lot too, sensory evaluation as well. And PLS have been used in neuroimaging data, and it's proposed or it has been applied to neuroimaging data by people in Toronto, and it's from Baycrest. So Randy McIntosh group, who is now at SFU, but when he was here, he developed, he applied PLS to neuroimaging data. Okay, so what is PLS? You might see this in some paper, and it could comes in different names. It could be partial least square correlation if they're specific, or sometimes they just call it PLS. But also be careful that PLS could mean many different things. So you would want to look closer into the paper if they show this. It could be PLS regression correlation. Sometimes it means PLS path modeling. So it could be different things. It also comes under interbattery analysis or co-inertia analysis. They're all the same thing. And the goal is to examine multivariate association between two sets of data.
Oh, is correlation same as analysis?
No, correlation is different from path analysis. So in path analysis, usually you have an assumptions of the path, right? So this variable A expects variable B, predicts variable C. So it has like a path, and you're testing that model specifically. Whereas for PLS correlation, you're just saying, okay, I have these two sets. How are they related to each other? Okay, so what does a PLS look like? So I'm going to show you two examples. One is with questionnaires of memory. So this is a short example with only a few variables. So here I have 1,059 participants. They could be grouped into 6 groups according to 2 factors. So there's the sex categories, the age categories, and we have 2 blocks of variables that we want to look at the association. One is the OSIC and one is the SAM. And I don't remember if Mariah covered this earlier, but this is from, again, from Brian's lab. So they look at mini object spatial imagery questionnaire, which examine like object and spatial memory. The other one is survey of autobiographical memory. So we want to see how related these are. And each of these comes in different items, right? So in OSIC, there are 7 items that measures object imagery performance, and 7 measures special imagery performance. For autobiographical memory survey, you have 4 different sets of items. So episodic memory, future thinking, semantic memory, and spatial memory. But what you can see is that they all involves multiple items, multiple variables. And these variables kind of goes into different categories as well. And they're like measuring something different. So we put these two into PLS. And what we want to see is we want to find how they're related to each other. So what PLSC does is that I will create new variables based on these 2 tables, and I'll represent the people again on this dimension that captures the most association between them. And I can plot the people again. So now I could see group differences. I have the male group standing out from the other groups. And when I looked at like how related they are, we looked at the loadings. So if they're positive, if they're on the same side, it means that they're all correlated on this dimension. And when they go on the same side here and there, it means that this dimension is capturing just the general association between everything here and everything here, right? You don't see any separation. It just means the better performance you are on these, the better performance you are on these. So everything contributes to this dimension together. So this is a short example with just behavioral data. The other one I want to show you with a larger set of data where we have imaging and also genetics data, where the two data tables include 791 participants that could be put into 5 stages of Alzheimer's disease. And the two sets of variables that we have are genetics information, so 134 SNPs that we know are related to Alzheimer's, and also another 10 measures like brain behavior measures. So in the brain behavior measures, we have things that improve, like that are positively related to cognitive decline, and the one that's negatively correlated to cognitive decline. And we can, oh, and then for the genetics table, we have genetic information in 134 SNPs, where SNPs are pairs of alleles on the chromosomes. So in combination, they could come in 3 different combinations for each set. So basically, you could categorize these into the ones that are the same. So that's homozygotes, or the one that are different, so the heterozygotes. And then these are just the SNPs that we have, and we know that are associated with dementia. So we include them and we code them as numbers. So basically counting the risk alleles we know to Alzheimer's disease. And we ended up with this table, right? 791 participants, 100 SNPs, and how their alleles are represented by the numbers. And then again, we could do PLS and see how participants are represented when we extract the dimension that captures the most covariance. And you see a progression along this axis where you see people goes from healthy controls and to the most severe Alzheimer's disease. And then we could also look at the dimensions that captures this. And this first dimension just in general captures the intensity of symptoms, as you can see from here, like the differences. And when you looked at what contributes to it, it's the variables that increase with Alzheimer's versus the one that decrease with Alzheimer's. And then you identify the genes that contribute to it. Does that make sense? Is there any questions so far? Do you understand PLS?
How is it? How is it differs from PA?
It's similar to PCA, but PCA works on one data table.
Okay.
PLSC looks at the relationship between two. Yeah. Oh, okay. Can you run a PLS now? You're so confused? Yeah. Wait, what? I'm so confused. What do you mean? Okay. Now I'm going. You're supposed to be confused because usually that whole thing is what you will hear like at a conference when people present their PLS results, right? They're like, oh, these things are associated with this. And this is what we see. And this is PLS. And you're like, what? Okay. So I'm going into what PLS is actually about. And hopefully we'll come back to these examples and you'll understand better what I meant. If you find like the past 10 minutes confusing, it's supposed to be confusing. You're not supposed to understand anything I said. Okay, so that's normal. Okay. Ready?
Yes.
We're going to get to some math. Okay. But you're going to be fine. So coming back to partial least square, it's an extension of PCA. So it's similar to PCA. So let's start from what is a PCA, principal component analysis. So imagine we have a data set. We have observations on the rows, variables on the columns. So like an Excel sheet, right? You have your data that looks like this. What PCA does is it extracts a set of what we call the factors or principal components. Some people call it dimensions, latent variables. It could be like it could come in any names, but here we're just calling it factors. So it extracts a set of factors that explains the variables the best. So these factors are made of a linear combination of the original variable. Linear combination means it's a weighted sum of the original set. So it means, okay, these are all my information, and now I'm just like combining them in some way that gives me the most relevant information. And that new variables, now I'm calling it a factor, right? And this factor, what is it? Yeah. So the factors and with the weights that I use to create this linear combinations that I call loadings together, that gives me the component, the first component. After I got this factor, I subtract every information that's captured by this factor from the original data. And then I repeat the process again to get the second one. And I just keep repeating that until there's no information left in my data. So you can see this step, I extract, I subtract, and then I extract again. So because of the subtraction, each factor is unrelated to one another. And that's when people tell you that, oh, these components are orthogonal, these components are uncorrelated. So it means that they explained different chunk of your variance and there is no correlation between them. So you could explain them independently. So this step of PCA is a deflation and the components are orthogonal. Wait, is there any questions so far with how PCA works? No? And now I'm going into the core method behind PCA, which is the singular value decomposition. It sounds like a big name. It is a big name, but it's behind many things. So in a lot of like machine learning methods or dimension reduction methods nowadays, this is the core method that goes into it to extract the most important thing and to reduce dimension for you. So for dimension reduction, you can think about it as like when we have the PCA data. Okay, let's go back to this. So originally, if I'm plotting this data set, what do you usually do when you plot data set? You put this on your X coordinates, this as your Y coordinates, and then you have a scatter plot, right? When you have 10 variables, you need 10 axes to capture your data pattern. And these axes are dimensions. But you can't just plot tens of like how could you visualize that, right? You cannot just have 100 scatter plot to go through your data pattern. So what we could do with PCA is we extract the factors. And because these are the important information, so I can just use the two factors instead of 10 to capture the most relevant information in this data set. So this is when people said dimension reduction. So we go from 10 variables down to just 2. So with PCA, it gives you the minimum number of dimensions you need to capture all the information in your data. And this is the same idea for all the multivariate methods. So now going back to the core method, like how does this work mathematically? So imagine again, we have the data set. The SVD, singular value decomposition, is that equation. If you're scared, it's fine. Like just ignore that. It's not important. And I'm going to help you visualize it. So what we do is we decompose this matrix into three matrices. There's this P and Q. They have long names that we don't need to remember. But what these matrices do is, for these two, they describe the rows and the columns by the components. And we stored all the variance here. So you can imagine I have like a scatter plot. So imagine I only have two variables. I have a scatter plot. The P and Q is doing the rotation to find the axis that explains the most. And the variance is like stretching it because it stores all the variances. So it's just changing how you view your data with a new axis that makes better sense. And that's basically PCA. So just for your information, these are called singular vectors. P is on the left, so it's left singular vectors. These are on the right, so it's right singular vectors. It doesn't make sense. Singular values in the middle. So with that, we could decompose the matrix into separate components where we could also reconstruct the data from each dimension. So from PCA, I get component one, but I could also reconstruct the data pattern from component one and tells me, okay, so from component one, the data looks like this. And from component two, the data looks a different way. And when you add them up, put them back together, it gives you the original data. So to me, it's like we describe it like a potato, and you cut it into slices, and when you put it back, it's another potato, right? But when you cut it into slices, like when they're fries, like they're independent from each other, right? When you flavored one fries, the others is fine. So that's that. And these are the factors of loadings. Remember the weights we have to combine the variables that's stored in this Q matrix. And then we can plot, we could use these to get the factors, remember, the linear combinations. And now these factors, the new variables, you could use them to plot the scatter plot and visualize the participants again in the space. Make sense so far? Any questions so far? Or are we already lost?
You have one scatter plot for each two components.
So you can represent a component with an axis, and then you just use the scores as coordinates. And so you can do a scatter plot for any two components. Make sense? And then, so this is the linear combination we have here, how we build the factors. But from the components, like, okay, they're distributed differently, but then what? What are these components, right? So we have to find a way to define the components. And that's when we start looking at the loadings. Remember the loadings that we use, like the weights we use to create linear combinations? We could use that to see what's actually contributing to building up these components. And that's how we will define the dimensions or the components. So for example, if my component one are mostly made up by all the age-related variables, then my component one is probably just age. If my component two now have like all the boys are here, all the girls are here, then my second component is probably gender or sex, right? So you do have to explain your component or define it afterwards, post hoc, by looking at distribution or looking at how the loadings contributes to the dimension. Make sense so far for PCA? Okay. So to visualize the loadings, we do like bar plots. So the ones that contributes more will have like bigger bars. So you will see like what is actually separating the people from this side versus the people from the other side. Okay. So for example, if you see in your observations, if your participants that all the younger people are on the negative sides and the older people are on the positive side, then this first component is probably age. right? Imagine when you're plotting an age axis, that's how it looks like, right? The distribution. So you will see something similar here, and the direction of these loadings will tells you how related they are. So the one that goes into this side will be positively correlated with all the other variables that go in the same direction. Make sense? Okay. And then you can do the same thing for component 2. And this is why it gives you orthogonal loadings from SVD. And also the factor score here, because of the orthogonal loadings, it propagates to the components too. So this is just telling you that with SVD, this one thing, it will gives you, so for example, if you're just running it with a code, usually SVD is just a function like SVD. And what it's giving you is these three matrices. And naturally, it will give you unrelated components that you could use to build back your data. So this is also a way to, for example, reduce memory. Sometimes people found storing that one single big data table is too much for their memory. And so they would like decompose that into smaller matrices like this and store them so that later on they can reconstruct the data back. Okay. So that is PCA. And then we extend the similar ideas to PLSC, which is our main topics today, the partial least square correlations. So in PLSC, we looked at 2 data tables and we look at their association. So what we do is we compute pairwise correlation between each variables. Make sense? So this is a correlation matrix between all variables from this X and all variables from this Y. And let's just call it R for correlation matrix. And then we do the same SVD that we see in PCA. So what that does is that from these 2 sets of variables, PLSC extracts a set of factor scores respectively from each of them. And these factors are the linear combination of the original set of variables. So far, similar to PCA, it's just now applied to two data sets. 2 sets of data of variables. In PLSC, we call the factors latent variables, and it's just like they're developed differently from the traditions of the PLSC crowd. They prefer latent variables. So, but again, you will hear different names: latent variables, factor scores, dimensions. Like it comes with many names, but sometimes it's worth going into details and when you read a paper to understand what they really mean when they said latent variables. And this pair of latent variables from X and from Y need to look as similar as possible to each other. And by that, I mean they need to have maximum covariance. So what this does is that I'm extracting the most related information to Y from X and the most related information to X from Y. And I'm making that into a pair, a set. And this is my first dimension. So my first dimension is supposed to explain the most covariance between these 2 sets of variables. So it's describing the association. Make sense so far?
So at this point, when things are grouped, it's not correlations within X or correlations within Y, it's between correlation between the 2, and they get grouped that way. Like it's not, they're not correlating within X to create a factor, right? It's
no, but yes. But imagine this, if something here is highly correlated with, say, most of the Y's, then you will probably find another one that's highly correlated with this variable that's also correlated with Y, right? Because for correlation, you're looking at a pattern. If, say, the first variable here has a pattern similar to most of the y variables, then another variable in X that has similar patterns to this variable will also be highly correlated with the variables in Y. So usually when you do this, yes, it's based on the correlation between the like X and Y, but you should also extract variables that are just highly related within the block. So it doesn't make sense that it isolates like single variables, right? All the variables that describe similar things should be extracted together. And that's why it's kind of nice because it not only looked at the correlation to the other set, but it also accounts for the correlation within the block or within the data set. Okay. So I have the first set. I subtracted from the two, and then I get the second set that explain the second largest covariance, and they're orthogonal to each other, and so on. So I ended up with a set of latent variables that are orthogonal to each other, and they explain the covariance between the two sets of variables in the descending order. That makes sense so far? Could you see how that relates to PCA? It's similar, and the core method is the same. So you also have the deflation. It's now that you're subtracting from the correlation pattern instead of the individual data sets. And to do all that, it's the SVD on the correlation matrix. And now, originally we have in PCA, we had all the loadings in Q, right? Now we have the loadings for X and P and the loadings for Y and Q, where you can use both of them to compute the latent variables. And then you will plot them together. And it should look something like this, right? Because it's capturing the covariance between the two sets. Remember, if you want something looking like that they're correlated, it's showing like across the diagonal, right? And imagine if you're plotting two things that are correlated with each other, just a correlation plot, they should go in this line. So the first dimension of PLS is capturing the maximum covariance. So usually you will see this pattern when you plot the two latent variables together. Make sense? So far? And then to define what these components are, we again look at loadings, right? So now when people, because you only have people here and here, right? And it mostly goes in this direction. So all the variables from X that goes on this side means it's positively correlated with all the variables from Y that goes on the positive side as well. And everything that goes in the negative side for X is correlated with, or positively correlated with the one that also goes on negative side for Y. So you look at the direction. And also the direction of your loadings in PCA or in PLS, it's arbitrary. So you could run in one computer and it shows up a positive, and another computer it shows up as negative. But that's totally fine because you don't really interpret the direction, you interpret the relative directions. So you don't say, oh, this is positive, so it's positively correlated. No, it's like everything that has the same signs are positively correlated. Everything that have different signs are anti-correlated. So interpret the pattern instead of the actual signs of the loadings. Okay, so same thing for PLS as well. You could also compute means, group means on the latent variables, and then you could look at group effect there. So usually we extract some bootstrap confidence intervals for the means and looked at the confidence interval. If the confidence intervals overlap, that means that the two groups are not significantly different from one another. Makes sense so far? Yes. Yeah. Sorry? I wouldn't say multiple PCA. I would say it's similar to doing a single PCA, but on the correlation matrix between these two data tables. So PCA extracts not just one dimension. Like when you run a PCA, it's like that one SVD. So you extract the numbers of dimensions or components that captures everything in your data. Right, so you are going to end up with several components when you run one PCA. So it's similar ideas now. It's just that in PLS, the components are describing the correlation patterns between the two sets. Any other questions? No? Okay. And what's next? Is this one? Oh, it's just, okay. So in PLSC, the latent variable and the loadings together gives a component. And like the pair of components together gives a dimension. And also again from the PLS, because it's using the SVD, so you are going to get orthogonal loadings and it propagates to give orthogonal latent dimensions, latent variables. We're going to try again to go back to the examples. Wait, are you guys ready? Or is there any questions? Any other questions? No? Okay, let's go back to it again. So remember the two blocks with the object spatial imagery and the autobiographical memory? Right? So we take these two, we correlate them, and then we decompose this whole thing to get PCA. So what you should expect is you have a plot with the new variables created from each data table, and it should give you a new scatter plot of the individuals that captures the association. We could look at group differences by getting their means and like testing them with Bootstrap. And then we should see loadings that tells us what contributes to this dimension, and in general, what this dimension is capturing across these two data sets. Okay. With that in mind, let's go to the results. No. What is this? Okay. Okay, we saw this last time, right? Yes.
Both data sets should be in the same dimension.
No. No. So, okay, let me think how that would go. It doesn't have to be the same dimension on the column. So you don't need to have the same variables, right? Because you're relating different things. But it does need to have from the same people. It's just like when you do correlations. They have to, like the observations have to match. So that's the only dimensions that need to match, but the number of dimensions, it doesn't matter.
Of the values of the variables. We have like the variable, like that's a scale from like 0 to 10 versus another one's like 0 to 1,000.
Oh, great question, because you found something that I hide from you. Something I didn't mention. Before you do everything I said, you did standardize the variables, but we're going to go into that later, that how you decide how to do that, because it depends on the data set, right? I'll go into more details on that later. But so now we have here, we're showing the people again, but now on the first dimension. And you can see that it goes in this direction, right? The pattern. And this is normal. Like it should look like this because the first dimension is supposed to capture the most covariance in your data. So they should be positively correlated. And where did I show bigger? Yeah. So if I look at the actual group, you see the older female groups is, well, this is, no, 65 to 70 is significantly different from all the other groups. But the separation is more on along the autobiographical memory. If you look at the y-axis, they're kind of overlapping along the y-axis. So how you interpret these is by projecting the mean onto the axes, and it will tell you where they are on the x-axis, right? And then you have a clear separation along the x, so that means according to autobiographical memory, that's most related to 06, females between 65 and 70 have significantly higher scores compared to all the other ones. And then you can project them onto the Y again, and now you're looking at their 06 score, their new 06 scores. But they kind of overlap with each other, right? So it doesn't really separate the groups. Make sense so far? That side? And now we look at what contributes to this differentiation. Like, how do you define a component? So that brings us to the loadings for these. And you can see that all of them have positive loadings. That's why I said when I first show you this, that this dimension is capturing general associations. It's just telling you that, first of all, everything in OSIC is measuring similar things on this dimension, right? They all goes in the same direction. Everything from autobiographical memory is capturing similar information, probably just memory performance in general. And together, the most covariance you could find between them is just if they're doing well in autobiographical memory, they're probably going to also do well in the spatial and object imagery performance. Make sense so far? Any questions?
Can you explain what the circle is?
Oh, okay. So for the circles, it tells you how stable the group means are. So it gives you the confidence interval around group means. But you do it through bootstrapping. We'll go into bootstrap later. But basically you resampled and you looked at how stable this mean is. Okay. Any other questions? Okay, I have a question for you. Do you find this like extracting general association weird? Like I know people that are performing good here will perform good here as well. I probably don't need PLS to tell me that. Right. And so going back to a lot of the analysis, this is sometimes it's pretty common in PLS, especially if you work with like a patient data or an aging data set, that you always captures the strongest factor, that is age or just severity of your illness, and then that is the first dimension. And it's going to dominate your results. So sometimes we do go to the second dimensions, and that's when you start seeing different things. So from the second dimension on, you might be able to see differentiation between, for example, spatial will go in one side, object will go in the opposite direction. Okay. Okay. So second example, we have the SNPs recoded by counting the risk alleles, and then we have the brain behavior measures. And a warning here is that PLSC, just like PCA, correlation as well, They only captures linear effects, which means how I code the SNPs decide like the linear relationship I'm going to look at. If there is like a non-linear, like for example, a heterozygous effect, you're probably not going to see that because PLSC only captures linear relationship, right? Okay. So again, the two sets of variables, we compute a correlation. Oh, oh, oh no. And this is, sorry, this is what we see. So coming back to here, latent variables, you see they kind of are correlated. And if you take a closer look, there's better separation along the y-axis, which is the brain and behavior axis. And for the SNPs, I think you have clear separation between the healthy controls, which is just on the positive side versus the Alzheimer's. But like LMCI, EMCI, they're kind of like in between and they do overlap a bit with the two groups along like the axis. And if we look at what contribute to these dimensions, what made these dimensions, the loadings, you see that everything that increase with Alzheimer's severity is opposing everything that's decreasing with Alzheimer's severity. So this dimension, the first dimension, is just capturing the overall severity of your Alzheimer's disease. And that maps with this pattern as well. The interesting thing is that you do see things goes on different side in the SNPs that's related to the severity. So for some SNPs, the more alleles, like one of the alleles they have, the more severe you're going to get, and then the less alleles you have, the less severe you're going to get. So it's telling you that maybe some of these genes are protective. Some of these genes are telling you, are like, it contributes to your risk of having more severe symptoms in Alzheimer's disease. Makes sense so far? So negative loadings means that the direction is not important. The relative pattern is. So if you have something that has a positive loadings, it has an anti-relationship to everything that has a negative loadings. So for example, let's see here. We have hippocampal volume and ventricle volume, right, in Alzheimer's disease. And we know that as you progress in Alzheimer's disease, your ventricle becomes bigger and then your hippocampus becomes smaller. That's why they go in opposite direction, right? The smaller my hippocampus, the larger my ventricle is. That opposite pattern is described by one being positive and one being negative loadings. As opposed to, let's say, whole brain volume. So whole brain volume will decrease as Alzheimer's progress. And that's the same as hippocampus. Hippocampus will also shrink, right? So they goes in the same direction. And that's describing their positive relationship. Does that make sense?
Yeah.
And that applies here too. And these could become negative as well. So it's not like whether they're positive or negative that's important, it's whether they have the same sign or not that's important. Sometimes for interpretation or for visualization, you would want to have your healthy controls on the specific side. For example, I want to, in general, describe how severe it is. I want the severity to go from negative to positive. You can just flip this. That makes sense? Because the signs are arbitrary. I just found it confusing that the more negative it goes, the more severe Alzheimer's is. I think like that is, it just like when you describe it, it's a little tongue twisty. So I want it to be the more positive it is, the more severe it is. And when I want to do that, I just plot it in a flipped way. So you could, because the signs are arbitrary, you can just flip it. But remember, when you flip one, you need to flip everything. Otherwise, you will be confused with the pattern. So when I'm flipping the X here, I'm flipping the Y, I'm flipping the loadings of X and the loadings of Y, so that you can understand the pattern correctly. Yes.
I had a question for the labels. Are you just naming them yourself, or is there like a standardized way to name things like for example?
Oh no, these are the actual measures. Yeah. They're actually counting the values. Make sense so far? Any questions?
How would you explain the relationship between the loadings of Y and loadings? Did you do that, or you just looked up them separately?
No, it is going in the same way. So I explained the patterns here, right? It applies to this pattern between the X and Y. So you see that because most of the people are going in this direction, so I could say that the higher, like the SNPs, usually, well, when they're more positive, usually they're also more positive on the y-axis. That means everything that goes in the positive direction is positively correlated with the one that goes in positive direction in y as well. So the pattern applies to also looking at the associations between X and Y. So the higher you are in your loadings here, the more positive, it means the more severe you are in AD. The less severe you are in AD. So that means people that have these genes are more protective. Right, and then the people that have these genes are more risky. Alzheimer's people are more likely to have these genes than these genes. Does that make sense? So this is like a quick example of what you could do with PLSC. People also do that with like brain behavior. So if you have one table is your brain data. The other is your behavior data. You could look at brain behavior relationship. If you have two sets of brain data, you could also look at, maybe the associations between two states of your brain activation as well. Good so far? Okay. Now we're going into, but is there anything real in the data? So what I just showed you, they're descriptive. It's just like telling you, oh, the mean is this. Oh, there's a pattern like this, but there's a correlation, but is the correlation significant? So that's why we need inferential statistics. And so usually the first question we ask is how many components there are. Like, yeah, there are several components, but are they all equally important, or are some of them more important than the others? So that's why we go into looking at, are the components real? And we do it with null hypothesis testing using permutation test. Who remember permutation? Raise your hand if you remember permutation. 1, 2, 3. Did I get a 4? No. Okay. To remember null hypothesis testing. Okay. Can you tell me what null hypothesis testing is? It's test 101. Oh, Kube.
So like with the null hypothesis is kind of the hypothesis that we're trying to prove wrong.
Mm-hmm.
So like, let's say you're looking at like smoking and lung cancer.
Mm-hmm.
So your null hypothesis would be like smoking doesn't cause lung cancer, or is not associated with lung cancer.
Mm-hmm.
And like you're trying to essentially like
I don't think about this.
Yeah, you're trying to say you reject the null,
Yeah.
right? When something significant is like, oh, with this data, I think it's unlikely that the null is true, right? And you never prove the null. Oh, wait. You always fail to reject the null, but you never like accept alternative hypothesis. Remember this part? Like the tricky part in your stats 101. By the way, you're not supposed to remember everything in stats 101. That's how memory works. And yeah, so in all the analysis you do, ANOVA, z-test, t-test, when you compute a t, when you compute a z, you compare it with a distribution, right? It's usually at the bottom of your textbook. There's a table. You find the t-values. You look for the p-values associated with it. If it's less than 0.05, it's amazing, right? Remember that part? So the distribution that's printed on your textbook, the t distribution, the z distribution, that's a null distribution. And what it does is, okay, I find an observed value. I compare it with my null distribution. Null distribution means what the values should look like normally if the null is true. So if I find an observed value that is very unlikely, it has a low probability in the null distribution, it means that, oh, then I could probably reject it. That makes sense so far. So the t distribution, the z distribution that you're comparing to is a null distribution. And we're going to use that idea in permutation tests to tell us whether the components are significant or not, whether it explains a significant amount of variance or not. Other ways of deciding how many components are like Kaiser line. So Kaiser line is a guy named Kaiser, and he's like, okay, I think everything above this line is meaningful. Everything below is not. And I hope you could see how that could be problematic. But it's a criteria that we can use, right? There is a rationale behind that, but it has become more arbitrary, especially this is probably developed in the older days when they work with psychometrics data. There isn't that many variables. Nowadays, we have very noisy, for example, brain imaging data, right, that everyone's working on. And we probably need a new way to decide. Okay. The other thing we want to look at is we look at the pattern of loadings. We know how the patterns, but are they all equally important? Do they actually mean anything? Do I need to care about everyone? So we want to look at how reliable each of these loadings are. So are these bars significantly different from 0? We're going to use Bootstrap to look at that, and we'll go into more details of that later. The other thing is how important they are. That gives you the effect size. So we look at contributions, and contributions is the squared loadings. It tells you the amount of variance that each variable contributes to this dimension. And we look at who of these variables contributes above average. So just one thing to point out, being significant doesn't mean it's important enough, right? You could have something that's significant, but the fact size is so small. What is a common case that this will happen? Anyone? When would you find something extremely significant, but the fact size is so small? Does anyone hear that? Was it?
A big sample size.
A big sample size. When you have so many people, you're going to be significant, even with a very small effect size. And that is because significance or what we say, whether it's reliable or not, depends on 3 things. It depends on the effect size for sure. It also depends on the sample size and the power of your data. And that's why usually when you have a really big data set, any effect could be significant. right? And that's why it's important to look at both of them so that to avoid, you know, how do you say that? If you find something that's really small, maybe it's not reproducible. And that's the main issue with the reproducibility challenge nowadays, especially when you're working on big data sets. Okay, so let's start with the components and the permutation test. The permutation test. So it's a non-parametric test, which means we want to build a null distribution based on our data sets. The assumption of permutation is that what we collected, the data that we have now, is the best representation of the population. And we're going to see what the null distribution will look like if this is the best we could get. And what it does is permutation, permute the samples by breaking the bonds. So what that means is, for example, I have 6 people and they're measured on 3 things, right? The people have the variables are connected. Does that make sense? And what permutation does is that okay, let me just call it project then. What permutations does is that I break the link between these variables and shuffle it independently. So I put them into a hat, I shake it, and then I pull it out again. Okay, one by one. So it's without replacement. Right, I'm just changing the order of it. And then I change this order. So now I change it like that. So the phase changed. Oh, wait. So you see now I still order all the variables the same way, but the phase has changed. So if I want to look at how related the phase relates to these, now the links are gone. Right. So this, if I'm doing a correlation between their pictures and, for example, sex or age, now there's no association. So now the null is true, and we know it's true because of how we shuffled it. And when I compute a correlation, now it's going to give me a null distribution. Right. So the next thing we do is we repeat that many times, and I'll come back to this. And then if we want to correlate this with a PLS, we just repeat the PLS for each of the iteration. And at the end, we create a distribution. So what that means is, okay, I'll break it down a little bit more. In PLS, before we decompose it, remember I talked about you need to normalize the variables. When we do permutation, you need to pretend like the variables are still the variables that we put in. So, and this is just like a sample of our variable. So we're still normalizing it with the original mean and standard deviation. And so when we break it, we shuffle it, we do a PLS, it will give us one value, right? One loading values for each of these, and once latent variable scores. That gives us one value. I resample it again. I repeat the whole head things again, reshuffle it, do another PLS that gives me the second value. When I repeat all of them 1,000 times, I end up with 1,000 values. And with that, I can create a distribution. And because there's no relationship between these two, now the distribution is a null distribution. And I can compare what I found with my data to this null distribution to determine whether it's significant or not. Make sense? Okay. Any questions?
Yeah.
Yeah.
We didn't sample a lot of times, which means we shuffle the places in the hat and took it out. But if it's close to infinity, then will there be one time that the faces are actually correlated, are actually with the original data.
Yes. So that's why we are doing it 1,000 times. So, so with 1,000 times, you could create a distribution, and I'm here just plotting the distribution with histograms. So you can see that sometimes they have very high correlations. Sometimes they have very low correlations. But with 1,000 sampling, or you could do more, we want to achieve like a normal distribution where this should be the most likely, where the value most likely to be. Right, and that's just based on the central limit theorem. When you increase the sample size, it's going to approximate the normal distribution. So the really high correlation should be a rare case. And so does the really low one. If this is a null, but it gives you a null distribution. If your null distribution is high and has all the high correlations, it just means that when there's no relationship between the two, just based on the structure of the data or for some other reasons, it's going to be high. And that probably means you shouldn't be compare your value, whatever statistics that you're computing, with zeros. Instead, you should be comparing with the mean of the distribution. Does that make sense? So then we compare the observed value, and then we can count how many cases are larger than the observed versus the 1,000 case, and that gives us a p-value. And that's how p-value is computed. So the proportion of this over the whole distribution. Does that make sense? So across 1,000 sampling, I have, for example, five cases that is larger than my observed value. Then my p will be 5 over 1,000, and my p-value will be 0.005. Okay. So we look at dimension 1. This is what it looks like when p is 0.06. It means everything here compared to the whole distribution is 6%. Okay, so we do that for each dimension, and with that, we could determine whether the dimension explained a significant amount of variance or not. The next thing we do is we looked at how significant the loadings are, and that's when we do bootstrap. So bootstrap, let's go back to this again. Now bootstrap, we don't want to break the link. We want to keep them connected. So we keep the associations. And now, so see, we have the face going with the associations. We don't want them to break. And I shuffle them again. And then I start sampling from it. But now I sample with replacement. So I get one, I put it back. I shake again. I get the second one. And with that, you could have repeated observations. So what this is doing is that I'm assuming that my data that I collected is the best representation of the population. And I want to know if I sample in this population, how extreme my analysis could be, the outcome could be. So it tells me how stable this the results is. So again, we repeat it for 1,000 times, and then we do PLS every time, and we then build a distribution. And this distribution tells us how extreme the values could change based on our current data. From the distribution, we could compute the mean and the standard deviation, and then we compute a bootstrap ratio. Okay, so what we do is we subtract, we divide the mean by the standard deviation. And this is similar to computing a z value or a t value. And that tells us how significant the value is. Usually the loadings, right? How significant loading is different from 0. And how do we check significance is by comparing the bootstrap ratio to 3. And we use 3 because in brain imaging analysis, there are more variables, so we want to correct for multiple comparisons. Originally, we compared with 2 because 2 is related to P of 0.05. And that is because this is a value similar to like a Z statistics. And remember the Z value, the critical value of Z when it's 0.05? 1.96. Remember this number somewhere in your memory? 1.96, and it's very close to 2. And we're just like, okay, we just might as well say 2. So this is the value we use to determine whether it's significant or not. But in brain imaging, because we have many more variables, potentially we want to correct for multiple comparisons. So we just bumped it up to 3. And this, I think, associated with some p-value close to like 0.001. Any questions so far? Does it make sense? Like the difference between permutation and bootstrap? Is there anything I need to repeat, or you want me to repeat or explain again? Yes.
So is the main difference that with permutation, you're just reshuffling and resampling versus this one is replacement, but both one is to like look at statistical significance and then one is to look at all the line. Or is there more to it?
There's something that you're missing, but you got the idea. Like one is resampling with replacement, one is without, right? But another important thing is in permutation, you break the links. Right. The reason why in permutation it's a null distribution is because the links is not there anymore. And you can do the same thing with like coefficient of correlation, right? When you compute just a correlation between, for example, X and Y, when you do permutation for correlation, you shuffle the X so that now it's not linked to Y anymore. And even if it is, it's not anymore, right? And then when you just compute a correlation that one time, and you repeat that for 1,000 times by reshuffling it differently, you build a distribution when the null is true. So there is an important thing that in permutation you break the links because you're computing a null you're building a null distribution. Whereas in Bootstrap, remember, like before we put that into the hat, the phase are linked to the numbers, and that links doesn't go away. So in Bootstrap, it's just telling you how extreme this value can be based on the fact that the data we collected is the best representative of the population. Yes. No, Bootstrap is not parametric because it's only based on your own data.
No, but like calculating like the value and
So this is not really a t-value. This is it has a similar idea to a t-value. So okay, so I put t's here because some people will say it's a t-value, and it could be a z-value too because it's a similar idea that
yes,
you divided your mean by the standard deviation. But what makes it parametric is when you compare this to a t-distribution, a t-null distribution.
Yeah.
To determine your p-value.
But I thought that's what is on the next step.
When we're checking this, but this is also because when we have 1,000 samples, it should be normally distributed. So it's based on the central limit here.
And is this kind of test implemented in some model to see what it.
I
Without
think there should be
Okay.
there should be functions in R and Python that does permutation in Bootstrap, But when you understand this, you should also be able to write a function yourself to do that, right? And also, this is like the simplest version. There are other things that could comes into it. For example, if I do have a structure that I want to keep, for example, gender ratio. I want to have 2 to 3 male to female ratio, and I want to keep that factor structure. Then when I resample within the groups. That makes sense? So for example, the face I showed you, it has 3 males and 3 females. If I want to keep that balanced structure, I will just resample within the males and resample within the females to make sure that in my resample data, I still have 3 males and 3 females. So this is like something that you could add to the Bootstrap if you have a structure that you want to keep. Yeah. Any other questions? No. Okay. I think we're done with the math. We can breathe. Take a breathe. We're fine. We're good. Okay. So this is something important. I think I've covered it also, that significance does not mean important. So Bootstrap ratios tells you how significant it is, how different it is reliably from 0, but it doesn't tell you how important it is, which means how much it contributes to building your dimension. And with that, we looked at contributions where we squared the loadings, and it captures the variance that each variable contributes to the dimension. And with square loadings, they're additive, which means you could add up the square loadings, you could add up the contributions to get a group contribution. And this is useful, for example, when you look at brain data, you can add up the contributions of different voxels that belongs to the same network to get a network level contribution. But you do have to square it to add them. And then we compare the contributions to the 1 over number of variables because each of them contributes one amount of variance. And so with this, we could look at who contributes above average. And remember, you cannot do any computation on the loadings. You do want to square them. Question, why? Why do we have to square it to add?
Because they're positive.
No, not to make them positive. They cancel each other. No, not that. There's a theorem for that you need to square them to be additive. Anyone want to take a guess? Start with a P. Do you remember an equation that's a squared plus b squared equals c squared? Yes, exactly. That's why. Like, that is the basic behind all your statistics. Like, you're squaring things and adding them. Remember sum of squares that you hear a lot when you compute it. Sum of squares divided by n is variance, right? Why are you summing the squares, not just the values? Because of Pythagorean theorem that a squared plus b squared will equal c squared, but a plus b doesn't equal c. And that's the idea behind summing the variance, and that's why you talk about sum of squares a lot in statistics. And that's the same ideas here in the loadings. So we take the sum of squares of the loadings, and that gives us the variance. Make sense so far? Okay. Okay, so it is also common that people plot bootstrap and contributions at the same time. But just remember, in a lot of papers, you will see people showing you the bootstrap ratios But bootstrap ratios just tell you how significant they are. Like it's giving you the t-value. When you do correlation test, your statistics is F is your F value, right? When you do correlation test, it's an F test. The F is the bootstrap ratio you see. But what's describing the actual effect size is the R. Does that make sense so far? So sometimes people will be showing you the bootstrap ratio is just like showing you the F values when they do correlations and tells you how significant it is, but it doesn't tell you the effect size. For the effect size and correlation, you do the R squared, right? It tells you the amount of variance explained by the correlation. So that's just one thing to be careful about when you're showing a result from PLS. You want to show the contributions, the actual effect, and then you could put asterisks on it to tell us whether it's significantly different from 0 or not. And that asterisk can be based on bootstrap ratio. But it's kind of misleading if you're showing the bootstrap ratios because this doesn't show you the effect size. It just tells you how significant it is. Make sense? The other way of examining reliability, and now you're required to do this more and more when you do PLS, is you need to do cross-validation. It could be k-fold cross-validation. The common one is like 10-fold cross-validation, or you need to do split half. So similar ideas between split half and k-fold cross-validation. You're breaking your data into subsets, and then you repeat your PLS within these subsets, and then you compare how similar the results are. The idea is if you can find the same pattern in different subsets of your data, then it's more likely to be reliable. But if you only see the pattern with all the data, but when you go into the subset, it stops replicating the pattern, it could mean that you're just seeing this pattern just because of the current sample you collect. And when you start to collect more data, the pattern will change. That means when the pattern is not so reliable. So that's when people start to do k-fold cross-validation and also split half. And so other things to know about PLS is when we do permutation tests, there is an issue because remember when I talk about PLSC, when we extract components, we subtract the first component to get the second one, subtract the second one to get the third one, and so on, right? That means each components kind of depend on the previous component. And when we do permutation, when we shuffle and do PLS, they're still dependent on each other. So that means sometimes I shuffle it, I extract my first component, and then it's already different. It's already very different from my second component on to my real data. And so people sometimes don't believe any permutation test after the second component. Only the first component is trustworthy. Some people think that way. Now there are other like alternatives of fixing this problem, but we won't cover it today. The other thing is PLSC is immune to multicollinearity. So it's different from linear regression. Like if they're highly correlated variables, it's fine. Just like when you put all of that into PCA, it's okay. It's not going to affect the results. As opposed to another similar methods called canonical correlation analysis, or CCA. You might have heard of it. It will be affected by multicollinearity. So I actually wouldn't recommend analyzing brain data with CCA because they're usually highly correlated. Like you usually have your variables are usually voxels right next to each other, right? And they are highly correlated. In CCA, that's going to bring you a lot of noise unless you do some steps beforehand. So some people I know do they do a PCA first to get orthogonal components and then they put that into CCA. Yeah, but I would say PLSC is a better alternative because it deal with that for you. It's basically not affected by it. And the preprocessing step. So that goes back to your question about centering and scaling. If there are measures on different scale, what do we do with it? So centering means you're subtracting the mean. Normalizing means you're dividing it by the standard deviation, so removing the unit. And this is what you do when you compute a correlation, right? You always center and normalize so that you can compare them because you want to remove the units. And this is the same in PLSC. Before you extract components, you always center and normalize. And these are always, I think, default in most of the functions. So there are different ways of normalizing. You can normalize by doing having the standard deviation equals 1 or having sum of squares equals 1. But there are cases when you don't want to do that. So you do want to think about whether you need these steps or not. For example, centering is moving the zeros to the mean, right? And this happens when the zero is not important. The mean is not important. But there are times when in your data, you do want to keep the zeros. The positive and the negative mean something real, and you don't want to just change that arbitrarily. For example, if you're analyzing connectivity data, where positive connectivity and negative connectivity has a real meaning in real life, then you don't want to just center it. You don't want to just move the zeros to your mean. Because what that does is that some of your slightly positive correlations becomes slightly negative or even more positive. But that doesn't mean in your real data, they are more positively functionally connected, right? So when you're analyzing, I would say network data with PLSC, I would recommend not to subtract the mean. Just use the zeros in your data. For normalizing, when you want to do it is when all your variables are on different scales. But if they're actually from the same measures, then you probably want to keep that variance and you don't want to normalize them. So same thing for network connectivity between different regions, you probably don't want to normalize unless you don't care about the variance within the variables. Does that answer your question? Does that make sense? Yeah. So think about the variables that you're going to put into PLSC and think about whether you want to subtract the means or not, whether you want to normalize them or not. Are they using the same unit or do you have to normalize because they're on different units? And you do have to, if you're going the other way, if you're not centering or not normalizing, you do have to set that up specifically when you run the analysis because most of the function that runs PLSC have default setting for these. And some of them allows you to change, some of them does not, but you do need to be careful with that. Okay. What PLSC cannot fix? So first, it cannot fix overfitting. If you still have much less observations than your variables, it's probably still going to overfit. There are other things that you need to do to overcome these issues like regularization or feature selection methods. So if you have a small sample size, a bad representative of your data, or messy data, that your data is just not clean, PLSC is not going to clean it for you. The same thing just applies like garbage in, garbage out. What you give to the model is what you're gonna get. It's not going to get better. So don't use PLSC and think it's going to fix everything. Still check the quality of your data. The other thing is PLSC only detects linear effects. So if you're looking for nonlinear effects, you might want to go with other options that has like kernel functions that deal with nonlinearity. Also, if you don't understand your data, PLSC is not going to help you. So to be able to interpret the results, you need to have some understanding of your data. You can't just like throw random things into PLS and then interpret random things, because think about its correlation, right? Correlation is not causality. You could find correlation in crazy things. So just you still need to understand your data. You still need to select the variables that you want to correlate instead of just throwing everything into the model. Okay, so just quickly, there are different types of PLSC. There's one that you can compare between groups, basically like a contrast analysis, multivariate contrast analysis. And you could identify like the difference between different groups. Yeah. The other one is mean-centered text PLS. I think this is more common if you're using the Baker's toolbox for PLS. And this is doing group coding. So I'm only coding young people, middle-aged people, and mature old people. And here I'm identifying the features specifically related to specific groups. So this is mean-centered. You can see the separation on the latent variables. The other one that is related to brain analysis is seed PLSC, where where you have, for example, I picked this pixel and this pixel, and if you think about it in the brain, it's like this voxel and this voxel in a brain, and I want to look at how similar they are to the rest of the brain, the activation. So it's like a multivariate correlations to look at seed correlations. And I can find the features that's related to that's differentiating seed 1 from seed 2, or the one that's mostly contributing to seed 1, but not seed 2. Yeah, and then you could again look at the latent variables. And I'm also sharing, like, there's a tutorials I have for R. Let me pull it up. This is this one. Okay. So there's a tutorial I put together with a toy example on wine tasting, and it like goes through the outcomes of PLSC and the interpretations and what it means and everything, and also with code. If you click on the R code here, so you will see it. And the other thing I want to mention is I always recommend when you run any type of analysis, even just simple correlations, I would suggest you plot your data pattern first. So in PLSC, we usually plot the correlation matrix first. So you would expect to see something that show up in your correlation pattern captured by your PLSC component. The other thing that I could share is I will share with you an example code in R that I use to run PLSC. So it goes from visualizing the pattern to the actual analysis and then plotting the outcomes with some explanations. So you could follow the tutorials and try to run PLSC yourself. So coming back to this, there's also a manual for the MATLAB and Python packages developed by Randy McIntosh, that used to work at Baycrest. So they have help file the manuals here, and I would recommend if you're running this, their package is usually pretty good in running like brain data, but I would recommend going into it. Make sure you know if you're centering or normalizing your data before you get everything running, because they do have, I think their default is mean-centered PLS instead of just normal PLS. Yeah, so that was everything. Is there any questions? Thoughts? No? Okay, that's everything. Thanks.